Hi, hope you're doing well, and in this video, we're going to go over the physics reference tables for the upcoming Physics Regents exam. Now, I taught physics in high school for over 7 years, and it's been a little while. I just retired in October, so I'm a little bit rusty, but I think my rustiness is actually going to help you because there are certain parts that I think you need to keep in mind as you get ready for the exam and take the exam. So let's go through that now. And this is really a special video for my students of last year that took chemistry with me that are now approaching the physics regents here in the spring. All right, so the first table here on the first page are all physical constants that you may or may not need the day of the exam. Certainly acceleration due to gravity and speed of light in a vacuum. You probably already have those memorized. Those are definitely going to show up. Some of the other ones may or may not. Not only can this table give you some, obviously, the physical constants, which is great information. Not only can this table give you the constants, but another thing that if you get confused on the exam, check out the units. For example, acceleration due to gravity, acceleration's units, meters per second squared. Speed of light, speed and velocity is meters per second. Mass, kilograms, etc. This is very important. You need to recognize what variables you have and what units in order to figure out what formula you might end up plugging into. And with that, we're going to go to the back of the table for the mechanics formulas because you use those a lot this year. Well, here is the back page, and you have a long list of different formulas that you're going to be using on the test. For every variable that's here, you should know the unit or units associated with these variables. Well, what do I mean by that? For example, force. Force is in newtons. Yeah, but what makes up a force? Well, force is equal to mass times acceleration. That's kilograms times meters per second squared. It's those types of clues that are going to help you when it comes to actually figuring out what you're calculating on the test. The test is not easy. Most questions, if not all of them, are going to be multi-step questions, and you need to read and reread those questions along with knowing what the numbers are representing by looking at the words and the units. For example, let's check out question 4. You're asked what's the mass equivalent of 3.37 times 10 to the minus 19 joules. You need to remember that joules is a measure of energy and that mass is in kilograms. Well, actually, you can see that from the multiple choice. You won't be able to see that, though, when you're doing the free response type questions. Well, what's going to tie energy and mass? Let's go back to the reference tables. Now, I just arbitrarily picked out that question. One of the things you got to realize from that question is you have to be able to do scientific notation. And the easiest way to do that is let the calculator do the work for you. If you do not know how to work with numbers in scientific notation in your calculator, that is one of the number one things you're going to do before you walk in and take this exam. Find a video, ask a friend, ask your teacher, but you have to be able to do that. You don't want to make any mistakes. Now, we were looking for energy and mass. If I scroll down the back page here for mechanics, oh, wait a minute, here's an energy, potential energy type equation. Here's another one. Here's kinetic energy, right? Work done is equal to the change in energy total. You know what? None of these are fitting. Don't give up. Don't just force something in an equation. That means we need to move on. Mass and energy, mass and energy. Well, sure enough, if I just go to the page before, here it is, and E is equal to mc squared. Now we have an equation, but we need the speed of light in a vacuum. You don't have to memorize it. It's on the front of the reference table. And sure enough, if I go back to the first page, here it is all the way at the top. Again, you have numbers in scientific notation. You want to write everything out on paper, even when you're not showing your work. Don't just plug things into your calculator. You're going to make mistakes. You don't want to make mistakes. You got plenty of time for the test. Write it on paper, and then go ahead and calculate your answer. Try it now. Here's my setup. I have my equation. I plugged in the numbers on paper, and now I have to get the 3 times 10 to the 8th squared over to the other side by dividing. If you're practicing and you're finding you're forgetting about the square, then my advice to you is that you write out whatever numbers are being squared twice. You already know that 3 times 10 to the 8th squared is the same as 3 times 10 to the 8th times 3 times 10 to the 8th. But practice on paper. Very, very important. Another thing that you're going to be doing with all of those mathematical equations is at times looking at mathematical relationships without numbers being given. That means we're going to check out question 7. All right, for this question, we have an object traveling in a horizontal circular path at a constant speed. If the radius were doubled while the speed remained constant, what happens to the centripetal acceleration? Well, so I have circular path, constant speed. I'm dealing with the radius. Let's go back to the reference tables. All right, we're back in mechanics here, and centripetal acceleration is defined with the variable a and then a lower c. We want to find that equation. We're going to scroll down, and here is the relationship that we're going to check out with the question. We have centripetal acceleration is equal to v squared, so that's the velocity or the speed squared divided by the radius. Now that I wrote my equation down, let's go back to the question. An object is traveling in a horizontal circular path at constant speed, so the speed is not changing. All right, if the radius is doubled, so if we're going to do 2r, then what happens to the acceleration? Well, looking at the equation, what you have here is known as an inverse relationship. Since the denominator on the right-hand side is getting larger and the velocity is not changing, then the acceleration must be getting smaller. And if I double r, I'm going to have a. Now, you looked at an inverse relationship last year in chemistry. That was when temperatures was being held constant, the pressure times the volume of a gas was going to be equal to the pressure times the volume of the gas. And if one went up, then the other went down. Okay, so this is an inverse relationship. If I change the equation to be AC times R is equal to V squared, now it has, and V squared is remaining constant, I'd have just AC times R is equal to V squared, which is equal to AC times R. So again, if one is doubled, the other is halved. The other way you can work around this would be to set up your own numbers and plug those in and go ahead and calculate two answers using the same equation, but doubling whatever you use for the radius a second time. And then you know what ends up happening. For example, here I wrote the equation down. I set V to 1 meter per second squared and R to 1 meter. And when I solve for AC, I get 1. Now in the question, I'm asked if the radius path were doubled. So it's not 1 meter anymore, it's 2 meters. What happens to the centripetal acceleration? I'm going to plug in the same value for V and solve for AC. Well, 1 times 1 is 1, 1 divided by 2, and AC is going to be equal to 0.5. In other words, the radius was doubled and the centripetal acceleration was halved. that brings me to a very important point. Not only do you have to figure out what equation or equations to use, plug things in, get your answers, but you have to be able to look at equations and know what type of mathematical relationship there is. There is direct. Here are the four: direct, direct squared, inverse, inverse squared. And that just doesn't go for these equations, but again, any equations on this reference table. Make sure you know them. And then, of course, there are graphs where you would look at the two variables that was graphed and be able to pick out the relationship. We just did an inverse relationship between centripetal acceleration and the radius. The inverse graph, if you remember the inverse graph from chemistry, it looks like that. It's that curve. You need to know all four, though, here for the physics regions, because you do have a lot of squares going on, right? Even just in what you see on the screen, you have a square here for time, you got a square here, again, from the distance between two centered. I'm not going to give you all the information. Go look it up. So you need to know the different types of mathematical relationships and the graphs that go with them. One other very important point that goes along with any equation that you're going to use on that reference table. When you get to part B-2 and part C of the test, and you see in parentheses that you are supposed to show all your work, including the equation and substituting in with units, it is very important that you do that. Each one of those questions is worth 2 points. If you don't do all three, you're going to lose points. You might even lose all the points, even though you have the right answer or the number written down, but you didn't show your work with the equation and substituting in with units. And I mean all units. So for example, just taking a look at this particular question here, you're dealing with, different vertical speeds, right? A vertical speed and a horizontal speed in meters per second. If you made a mistake and just put in the speed as meters, you would lose points for the substitution with units because you don't have all the units. Again, it is very important. Now, what I like to do, and I'm going to show you with this question, is to literally write the equation down. Don't move the variables around in the equation. I don't like doing it that way. Instead, I want to plug in the numbers with the units before I move things around. Why? Because if I make a math mistake, I still might be able to catch the first point, even though I might not get the second point. That's just me. That's how I taught my students. Write the equation down, plug in the numbers with the units, and then go ahead and get your answer with units. All right, so 4, 56, and 57. Let's check this out. We're dealing with a projectile launched from level ground, has a vertical speed, right? Vertical means up, of 26 meters per second, and a horizontal speed of 15. The vertical speed is going to determine how long that the projectile is in the air. What goes up must come down. The horizontal speed is going to determine how far down the range of the projectile when it's going to hit the ground again. But for this particular question, we don't have to worry about the horizontal. We're dealing with the vertical. Now, it starts at 26 meters per second. It goes up the top of flight. You know that the speed is 0, and then it's coming back down. And since it's coming in an opposite direction, if up is positive, then we got a negative 26 meters per second coming down. You have 3 different ways you can go ahead and calculate your answer. You could do the up trip, and then the total time is up plus down, or 2 times up. If you want to avoid the negative, you can do the entire trip, which is going to be your answer. All right, but you do have to worry about the signs here. It's going to be very important. So we have a final speed we're dealing with, we have initial speed we're dealing with, and we're looking for time. And then, of course, we have acceleration due to gravity, our little g, that's on the front of the reference table. Okay, you have to know, and let me show you something else I want to check out. Early on, students will get confused between VF, VI, and then average speed, which is V with a bar, right? So we're dealing with VF, VI, we have acceleration due to gravity, and we're looking for time, and sure enough, what fits is right here. Well, here's my equation, right? This would go on the answer booklet. Now I'm going to substitute in with units. If I do the entire trip, if I'm going to do up and down because I want to get total time, then my final velocity is going to be 26 meters over seconds, but it's going to be in the downward or negative direction. Then I have 26 meters per second positive plus 9.8 meters per second squared times t. I'm running out of room here. But that whole substitution is what you have to have. If you're missing something, you're not going to get full credit. And then, of course, from here, you're going to go ahead and calculate your answer. See, I'm rusty too. And this is a good point. And that's why I like doing these reviews, because I don't have it ingrained in my brain. I forgot one thing: acceleration due to gravity. It's always pulling me down, man. Since my final velocity I'm putting as negative, don't forget my 9.8 or 9.81 has to be negative as well, because it's always pointing to the center of the earth. Now I can go ahead and solve for t. If you get a negative time when you calculate stuff, then you know you probably messed up the signs. I'm going to get a negative 52 is equal to a negative 9.8 times t. Now I'm going to divide both sides by a negative 9.8. And of course, that will get rid of the negative sign, which we're not going to have with time. So it's just 52 divided by 9.8 or 9.81, and we get 5.3 seconds. And that's our answer. You have to practice these questions. If you walk in without practicing, it's going to be extremely difficult. Do some work on your own, review with your teacher. I'm going to put in the description some good physics teachers and a good review of last year's exam. Go through them yourself. Just a final word about this first page. Sometimes what was helpful for my students that's not on this particular page was that average speed was equal to VI plus VF divided by 2. That seemed to work. Or remember that total distance or displacement over total time is equal to V. Okay, moving down the line, of course, AY, not AX. That's for any kind of vector at an angle from the horizontal, and your theta is going to be here. So you have, it's like taking the arrow and breaking it apart, right? You have, let me just switch the color. You have an AY component and an AX component. Alrighty. Let's see. This equation right here. Big G, the universal gravitational constant, is on the front of the reference table. You have to plug in all of the units. If you don't do that, you're not going to get it right. A lot of times you're also pulling maybe the masses of like the Earth and the Moon from the front of the reference tables and putting them in. And please recognize you have not just an R, but R squared here at the bottom. For momentum, let's check that out. We have, of course, momentum before is equal to momentum after. Maybe you have two blocks that are moving together. So you have the before and then you have the after. Remember, it's mass times velocity. And one of the things that I like to do here with this equation, right, impulse is equal to F net times T, which is equal to delta P. Don't forget that could be m for the mass of the object times the change in velocity. That this little piece is always missing, and then you're always given some of those parameters and you have to do the tie-in. So it's mass times velocity. Here we have some equations that have to do with the spring, force on a spring, potential energy of a spring. Here again, it's that centripetal acceleration and centripetal force. Then we're gonna end here with some of the energy stuff. And remember, work done is equal to energy gained. Work has the same units as energy. All right, I don't know what I was just going to say there. Most of the time, we are ignoring friction, but if we're not ignoring friction, that's where this Q comes into play, better known as internal energy, right? It's the jiggling, wiggling, and giggling of the atoms and molecules that make up a substance. And then, of course, power. That's work done divided by time. From mechanics, we typically went into electricity next. And so I went ahead and I went back a couple of pages here to electricity. This first equation is the electrostatic force between two charged bodies. That's the Q1 and the Q2. It's the same setup as gravitational force. The K value, you're going to find that on the front of the reference table. Your charges, it could be the electrostatic force between two electrons. Now, in that case, because they are like charges, they're going to repel. Or if it's an electron and a proton, since they are opposite charges, they're going to attract. So electrostatic forces have attraction and repelling forces, right? When you have mass, those forces are going to always be attractive. Now, a couple of other things here. Big equation is Ohm's law, which V is equal to IR, or New York State has it listed this way. R is your resistance. There is another equation for resistance. It's right here, which has to do with the substance or the element that makes up the wire, the length of the wire, and of the, where is it, this cross-sectional area, how fat or how skinny the wire is. There is, for resistivity, a table here on the reference tables where, we'll take a look at that in a minute, but that's a different way to calculate resistance. You have to go with what's given to you in the question. For current, that's also known as the charge per unit time. And for voltage, I call voltage essentially, it's the kind of like the change in energy, right? Work over charge. All of these have units associated with it. I would go ahead, if I was you, and write them down, make sure you know them, so that when you're practicing questions, you can pull them out and pull the right equations you might need. Then we have a bunch of power equations here and work. Now, besides just straight electricity questions, there's circuits, right? There's where we have the wires, some sort of power source, and usually little bulbs or something that we're powering. We have two types. We have our series and our parallel. And here they are, my series circuits. Lost my thing here. The current remains constant. For parallel, the voltage or the push of electricity stays constant. More than likely, you're going to get a parallel circuit and you're going to have to go ahead and do some sort of resistance, total resistance type question. Why? Students get it wrong. They can't handle the equation. We're going to look at the June 2023 Regents and see if we can find the question or if there was a question, and we'll go ahead and check it out. Before we leave here, though, here is our resistivities table. Remember, that's that kind of script P that we're going to use in the resistance equation. If we're comparing the different metals or materials and their resistivity, for example, which one is going to be the best one to use when it comes to lowering the resistance, right? And why do I say that? Let's go back for a minute. If we take a look at this equation, the resistance of a wire and the resistivity, or whatever it's made of, is a direct relationship. If your resistivity is higher, then your resistance in the wire is higher. For example, your length. The longer the wire, the more resistance. It's a direct relationship. But check it out. Look at the cross-sectional area. Resistance and cross-sectional area is an inverse relationship. So in this case, the bigger the fatter the wire, the less resistance. You do have to be careful with that. Again, what am I doing? I'm looking at the mathematical relationships of the different variables within the equation. You could certainly be asked stuff like that. In the case of this resistivity table, all of them are 10 to the minus 8. So which wire is going to give us the greatest resistance? Here it is. It's the nichrome wire. You might have used this for the flame test last year in chemistry. Which one is going to give us the lowest resistance? That is going to be silver, right? Because this number is the smallest of the set. The biggest of the set is nichrome, more resistance, and the lowest is silver with less resistance. If you're asked to draw a circuit in part B-2 or part C, here are the symbols that you would use. All right, let's take a look at that question I was talking about. Sure enough, I found it. And it is here, right in question 5354. Calculate the equivalent resistance of a circuit. In other words, the total resistance. You take a look at the circuit, it is a parallel circuit. How do I know that? Well, if you take your finger and you start from the energy source and you start moving around, as soon as there is a fork in the road, so to speak, it's going in two directions, it's got to be parallel. For a series circuit, if I draw one of those, not very well, but I'll draw it, series circuit is always a loop, right? I don't have to lift my finger or I have to split anything. Again, the series is in one loop, parallel, you're going to have splitting. All right, what do I have? I have two different resistors here. One is 3 ohms and one is 6 ohms. And we're asked for total. Since it's a parallel circuit, we have 1 over Req is equal to 1 over R1 plus 1 over R2. Now, it doesn't matter. I'll make this R1 and this R2. And now I have to go ahead and plug it in and solve. This is where students can make a mistake. Remember, plug in your numbers with your units directly into the equation as it's written on the reference table first, so at least you're going to get one of the 2 points. So 1 over Req is equal to 1 over 3 ohms plus 1 over 6 ohms. Oh no, now we're dealing with fractions. Yeah, we are, but guess what? You have a calculator. So we're going to keep it. This is this, and this is what you need to get the 1 point. To get the second point, we need the final answer. What I would suggest you do is do 1 over Req next is equal to, literally take your calculator. In my case, I'm using my phone right now. 1 divided by 3 is 0.3333, so I'm going to make it 0.333 plus 1 divided by 6 is 0.1666, so I'm going to just do 116. Now, I don't just add these up. So my 0.333 plus my 0.166, and I get an answer of 0.499. Oh, that's my answer. No, it is not, because remember, it's 1 over Req. Now I have to flip it, right? So I'm going to take my 0.499 divided by 1. I'm going to go ahead and flip that, just like I'm going to flip the Req. So Req is equal to 1 divided by 0.499. And when I go ahead and I take the inverse of that, or just literally put in 1 divided by 0.499, I get essentially 2. So the answer isn't just 2, right, folks? It's 2 ohms. It's not a hard question, but you have to practice. And more than likely, you're going to see it again. So make sure you practice. And you can practice questions over again. You don't have to go looking for another one. If you made a mistake, fix your mistake, leave it alone, and come back to it the next day, a couple hours later, and do it again. And lo and behold, you're going to be making less and less mistakes, and you're going to get more and more things correct. Okay, so we're checking out waves here. Once again, you have a set of equations, and all of these can be used, maybe not all of them on one test, but you're going to be tested on different things. So you never know what you're going to have to go ahead and recall. I do want to point out, of course, that velocity in this case, your speed of the wave here, remember V is also equal to D over T. And let's take a look at question 28 on the June 2023 Regents exam as an example. All right, we're taking a look at question 28. By the way, waves has a lot of terms or terminology you should know, including the parts of a wave, like trough and the crest, amplitude, etc. Make sure you go over those vocabulary words. All right, for 28, what is the wavelength of a 300 hertz sound wave? Now, there are sound waves, and then, of course, there are your electromagnetic waves. In this case, sound wave and air, you have to have a medium in order to have sound. And we go back to the reference table, we take a look at the equation at the top, and we have that speed or velocity is equal to frequency times wavelength. That's the one we're going to need for this question. Remember that with frequency, the unit is a hertz. Hertz is equal to 1 over seconds. And my wavelength, of course, is going to be in meters. So meters times 1 over seconds gives you the meters per second. Now, in this case, it's the speed of sound that you're going to find on the first page of the reference table. It's listed as 3.31 times 10 to the second meters per second. And we're going to plug in the 300 for the hertz, and we're looking for the wavelength. So it's literally 331 divided by 300, which is going to give us choice 2 as the answer. But notice again, you got to deal with scientific notation. You have to deal with the front of the reference table, the constant, knowing that you need the speed of sound, and knowing what equation to pick. Nothing is a given on this test. I've already told you that, but here's just another example of that. I did want to show you one other calculation from the waves section of the reference table. And here in question 7778, it's asking for the angle of refraction of a light ray in air. If we take a look here at the diagram, we have a ray of light, we're given the frequency, we're going from flint glass into air. You'll notice the angle of incidence is 30 degrees. Okay, so the angle of incidence is going to be equal to the angle of reflection. And everything is always measured from this normal line, which is the dotted line. It doesn't really, you would draw it in if you need to, if it's not given to you. Okay, that normal line is going to be perpendicular to the different types of medium. Okay, when it comes to refraction, you're going to go ahead, it's going to either bend towards the normal line or away from the normal line, depending on, again, what's going on with the medium in this case, flint glass to air. In 7877, you're asked to calculate the angle. Well, we have these two pieces of information. We have to go find that on the reference tables, and we do have the angle coming in. We need what's called Snell's law. Let's go find it. Let's go find this other information, and we'll go ahead and show you how to calculate it. Okay, so the first thing here is the equation that we need. Snell's law is right here. And the index of refraction, again, we have flint glass and we have air. The flint glass is hitting at an angle to the normal of 30 degrees, and then it's going from the glass into the air, and ultimately what we want to do is calculate the angle of refraction. Below the electromagnetic spectrum, we have our index of refraction. These are our N values. And again, we're looking for flint glass versus air. We need those two numbers. Once again, we're going to have an equation where we have the 3 of the 4 parameters, and we're going to solve for the 1. Let's bring it all back. Here is the setup. Now, I like to tell students, especially when you have something like this, it's similar to the titration equation from chemistry, in that for that equation, you had the acid on one side and the base on the other. In this case, we have the flint glass on one side, the air on the other. The 1.66 came from that table. The sign at 30 degrees, the 30-degree angle is given in the problem. And notice I have a little degree symbol. That is your unit. If you leave it off, there's no guarantee that you would get the 1 point for plugging in with units. Your indices of refraction, you don't have to worry about units. There is no unit, but there is for angles. And that 1.00 for air on the right-hand side is going to be times the sine of theta 2. Now we have to go ahead and solve for theta 2. Well, the first thing you're going to do on the left is you need to go ahead and figure out for 30 degrees, and make sure you have your calculator in degrees, not radians. In fact, when you walk in to take the test, make sure it's in degrees. I'm going to take the sine. Hold on. I'm trying to do it with my calculator right now. And I need to multiply it by 1.66. And I'm going to divide by 1, but then I got to take 1 over the sine because it's in the denominator. So second function, where are you? Oh, I'm using the calculator, and it's not my favorite. I need my scientific calculator for this one. And the answer is 56 degrees. Again, don't forget the little degree symbol. And yeah, that's your answer. And I'm just double checking. I don't see whether they would take off for it or not on the answer key, but let's keep it simple. If it's an angle, put the little degree symbol, right, that little 0 after the value. I know it's repetitive, but you got to practice questions. Even if you do them and you've got them right before, make sure you go back and practice them again. There are only June Regents exams for physics, so there aren't as many questions out there as there are for chemistry, bio, and earth science. But there's plenty of years now that we have questions. The more you practice, just the easier it's going to become. Let's move on to modern physics. Well, photons. Let's just talk a little bit about a photon to begin with. A photon is a discrete amount of energy. There is that duality of nature that you should have spoken about, not just in physics, but chemistry too. That tiny bits of matter on the order of an electron, and then tiny bits of energy. They possess some of the same types of properties, particle properties and wave properties. The Planck's constant, yes, it's a constant, and maybe you already guessed it, but that is on the front of the reference table. So is the speed of light. which of course the speed of light is also here in waves when we're talking about the electromagnetic spectrum. So when it comes to modern physics, again, I can use Planck's constant times the frequency for a particular bundle of energy, or it could be Planck's constant times the speed of light divided by wavelength. There's also the connection between what's going on with electrons in an atom, right? The change of energy levels and the energy either absorbed as electrons move out from the nucleus or released as electrons drop back down. This equation here is going to be related to two things on a different page. I'm talking about energy levels diagrams. On the reference table, you have the energy level diagram for hydrogen and an energy level diagram for mercury. If you recall from chemistry, every element on the periodic table has its own energy level diagram based on the number of electrons along with the number of protons in the nucleus. So we're looking at the different levels here. So if we're talking initial minus final for the energy of a photon, again, it could be from the ground state to the excited state, or from an excited state back down to the ground state. All right. And we have this whole idea of electron volts now, not just talking about joules. Do not let this throw you off. Let's go to the front of the reference table and I'll show you why. I've circled the conversion between electron volts and joules. They're just different units of energy. Examples of a couple of questions that might come from modern physics. If we scroll down the June 2023 exam in 63, it says determine the amount of energy in electron volts now that must be absorbed by a hydrogen atom to excite from n is equal to 1 to n is equal to 4. You're literally going to go to the reference table, start at 1 and go to 4, and then the difference is the amount of energy. I think that makes sense. I would highly recommend on the exam, you write all over your reference tables, they're yours to use. I just went ahead and rewrote the equation because there is a sign here, and a lot of times kids can get tripped up with the negative sign. We're looking at going from n is equal to 1 to n is equal to 4. So we got to make sure that we have the right value here. The initial electron volts is a negative 13.60. So I'm going to put that in. I know it's going to make a mess, but that's okay. Minus, now we got to go to level 4. So this is 1, 2, 3, 4. So that's a minus 0.85. Remember, a double negative is a positive, or really simple, plug it into your calculator. Exactly how you have it. So the 13.6, again, is negative minus, and then when you put in 0.85, change the sign to negative, and you're going to get your answer. That answer is a negative 12.75 electron volts. Let's take a look at 65 as another example. What type of electromagnetic radiation would contain photons each having an energy of, and here's the energy. Well, this also introduces another reference table, the electromagnetic spectrum. So let's go back and take a look at what we need. Here is the electromagnetic spectrum. Depending on the energy that we have the wavelengths at the top and the frequencies at the bottom. And you'll notice as the wavelengths get larger, the frequencies get smaller, and vice versa. Remember, we were given the energy, and I either need a frequency or the wavelength to figure out where on the electromagnetic spectrum that energy lies. Personally, it's just easier to use the first version here and get the frequency right? H is Planck's constant. We're going to get that off the front of the reference table, and we're given the energy in the problem, and then we have to go back and take a look at the electromagnetic spectrum. All right, 65, here's our E, that's going to go here. We got to get Planck's constant, that's going to go there. We're going to solve for frequency and then go to the back to the reference tables. Of course, we're dealing with scientific notation again, so please make sure you understand how to use it with your calculator. I just wanted to show you I substituted in, here's E, here's Planck's constant. We're going to divide Planck's constant on both sides. Yes, we have the dreaded scientific notation, and let's figure out the frequency. I get an answer of just about 4. If you round it, it's like 4.00 times 10 to the 13th. Let's go back to the reference tables. Our frequency, 4 times 10 to the 13th. Let's take a look at it. I'm not dealing with wavelength, I'm dealing with frequency. Of course, 4 is between 1 and 10, and this kind of goes by 1 times, right? So I'm looking at closer to 1 times 10 to the 13th, which is here. And when I go up, it hits the infrared part of the spectrum, and that's our answer. Moving to geometry and trigonometry, you've used this throughout the course. I really don't need to talk too much about it. When you're dealing with graphical motion, for example, let's say it's a D versus T map, and you have some different parts, you might have to look for the area under the curve, and you could go ahead and use rectangles and triangles. Of course, if you have anything with circles, you're given area and circumference, and then your right triangle. Of course, you have the Pythagorean theorem here, and sine, cosine, and tangent. Don't forget, it just helps sometimes to remember that you got the 3, 4, 5 triangle. You don't even have to use Pythagorean theorem if you remember that, or multiple of those. So, for example, if you had 30 and 40 for the two sides, then you would know the hypotenuse, for example, is 50. All right, with modern physics also, in physics, we go beyond just protons, neutrons, and electrons, and anything that has to do with the standard model or classification of matter, you're going to want to have this open. Okay, leptons, the key subatomic particle that you want to remember as far as leptons is the electron, but there's other ones as well. And then it turns out that protons and neutrons are made up of even smaller bits of matter known as quarks. Here in question 33 is an example where we're going to go ahead and use those tables. An antiproton has a charge of. You don't have to memorize it, just have to know where to look. Let's go check it out on the reference table. I come to the particles of standard model table, and of course, I forgot. They're not listing protons and neutrons here, they're listing quarks and leptons. And what do we remember from chemistry? We remember that a proton is positively charged. Well, you do have something here that's going to help. And it's this little note on the bottom. And it says for each particle, there is a corresponding antiparticle with a charge opposite. Well, what's the opposite of positive? Of course, it's negative. And that's going to be our answer. We used the table indirectly, but we got to the correct answer of choice 4. Let's take a look at one more here from the June 2023 Physics Regents exam, and that's question 64. Determine the sign and the magnitude of the net charge in coulombs of a particle that has a quark composition of BBB. We need the table now to figure out the charge for each one of those quarks, and then we're going to go ahead and add them up. Double check if they're not in coulombs. We'll switch it to coulombs, and we'll have our answer. I circled the bottom quark and each one has a negative 1/3 charge. So it's 1/3 plus a negative 1/3 plus a negative 1/3. Look, if you got to use your calculator and divide 3 into 1, go for it. But all we're going to do is the denominator stays the same, and we're adding it up, so we have a negative 3/3, which is in minus 1, but it's 1e. That means we need to go and do the conversion, remember, is we want it in coulombs. We are back at the front of the reference tables, and we want one elementary charge, or E, to equal coulombs, and sure enough, here it is. That makes, since it's a negative 1e, we would put it as a negative 1.60 times 10 to the minus 19 C. Remember, it's a negative 1.60 times 10 to the minus 19 C. If you forget the minus sign on this question, you're not going to get the point. I just double checked the answer key. So it's very important. They said net charge. Make sure that you go ahead and you have that negative sign as well. All right, we're almost done with the reference tables here. Remember, we have our physical constants, and the great news is you're given symbols and units. Use those to your advantage. Here at the bottom of the first page, you have, of course, your metric prefixes. If you forget any of them, usually I find that students don't really look at this too much, but it's there if you need it. Now, coefficients of friction. We haven't talked about this. These, of course, go along with an equation on the back of the reference table when we're dealing with forces. And what I just want to point out to you here is that you can easily see your static numbers or values are higher in comparison to the kinetic component. No units for these, and static means you're starting with some sort of object at rest versus kinetic where the object is already moving. And if you've ever kind of pushed a box across the floor and it's pretty heavy, you know it takes more force to get it moving than to keep it moving. Let me just show you what equation goes along with this. All right, we're at the back of the reference table, and it is right here. Okay, that the force of friction is equal to, right, the coefficient of friction times the normal force. So your normal force is, of course, what's getting pulled down by gravity, for example. There are times where you might be asked about force of friction or normal force, and you think you're using this equation, but it might just be some sort of F-net scenario. But certainly, if you're given a surface, two surfaces, remember, when they're touching and one or both are moving, you're going to have this coefficient of friction. Well, if you've made it to the end with me, good for you. I hope you got a couple of tips. I hope you feel a little more confident. I hope you have a little bit more time to practice questions. That's very important. I just want to give you one more tip here. You have these two equations. And remember, this is when you have an object, okay, that's moving horizontally. And let's say, I don't know, let's say this is a wagon and I'm pulling on the wagon. All right, my net force, of course, is going up and across. All right, and that net force in this example, letter A, can be broken up into the two components, the y and the x component. And you'll see the letter A means any vector quantity. So typically it's force, but it could be used, for example, for velocity. Now, these two equations are different than when you have an object that is on an incline. Okay, literally the pictures are different. And by the way, you can always draw yourself that free body diagram. I would highly recommend it. In this case, you have your normal force, which of course is always pointing down. If the object is at rest, right? We have a force of friction, and that force of friction is balancing out any force that might be pulling the object down. The reason why I'm bringing it up, right, there's that angle here, which corresponds to the angle here. So if you have to break up and figure out your normal force and your force of friction, now you're not going to use these two equations. This is only for on the horizontal. To use the ones here, right, we have FGX, force due to gravity, X, and force due to gravity, Y. And that's, of course, the force due to gravity, and it's flipped. So the X is going to be now sine theta, and the Y is the cosine theta. Okay, so the sine and cosine are flipped when it's on an incline versus when it's on a horizontal. All right, I'm just inserting a quick clarification here, right? No matter what, whether we have an object on a horizontal or on an incline, the force due to gravity, known as our weight, is always pulling to the center of the Earth. Now, we're breaking this Fg up into the X and Y components, depending on what we're asked. The normal force is always known as a support force. And if I have this box resting on this incline, okay, the box is pushing on the surface and the surface is pushing back. Hence, right, the normal force. And if this object is just sitting here, it's working against force due to gravity in the X, and that means that the force of friction and the force due to gravity in the X are canceling out. So the whole idea of taking the weight of the object and breaking it up into X and Y components is if you need to find the normal force and or you need to find the force due to gravity. Okay, so here, opposite the normal force, this is going to be our FGY, and here, opposite the force of friction, is our FGX. And yes, the sine and the cosine for these is opposite the sine and cosine equations when you break up a vector quantity into x and y components on a horizontal surface. I hope that clears it up for you. Look, as I mentioned at the beginning, I'm a little rusty myself, but that's a good thing because that means that I'm more inclined to go over some of the details where you might get stuck. Where if I had been teaching it over 20 years, I'd be like, what do you mean you don't know this already? Let's get back. I don't think you're going to see this. I actually texted Mr. Sita for those that are at the high school, and he said it's still on there, but it hasn't shown up in a while. I just don't think it's going to show up. This would be the least of your worries if you feel that you need to continue to prepare practice questions, have your reference tables out, have a sheet of paper, have your calculator, and literally crunch through things. I wish you all the best and good luck.